A quick search for flatten the curve is going to bring sorts of interesting memes that have popped up throughout the last couple of weeks, and this term has really exploded in terms of, oh, I like this one, really exploded in terms of popularity. In fact, if you go to Google Trends, which shows you the number of times that this search term has been used, it's really started coming out of nowhere the first week of March. Seems to have had a peak. People seem to have been losing interest, maybe because they don't understand the mathematical concept behind what that phrase actually means. Sounds nice, but let's actually talk about the mathematics involved here. So if we look at the world right now in terms of coronavirus cases, you see this quite disturbing graph. We have what is clearly exponential growth from here to here, and it looks like possibly this is a linear sort of pattern right around here, but it's not really clear until we see what happens next. So what's meant by flattening the curve or bending the curve is going to make a lot of sense if we look at the graph of a country that has nearly eliminated the new cases of the virus. So China is a perfect example of this. Let's take a look at China's data. Okay, so at the beginning, long ago, we had this steep exponential growth for the first month or so in China. Things started to happen around here. This is what we refer to as bending the curve. This is what lots of people say when they mean bending the curve. As you can see, the exponential growth stops becoming exponential. At some point it becomes linear, possibly around here, and then at this point it begins to curve so that it's concave down is the mathematical phrase for that. Then what you'll notice here is that the curve almost becomes flat, almost like there's a horizontal asymptote here, right? If we're talking, this graph is the total confirmed cases, or the cumulative confirmed cases. It makes sense that this curve starts to become flat when we have very little or even no new cases that are popping up. So can make that more clear by looking at daily new confirmed cases. So this is, instead of looking at the total cases in a country, we can look at just the new cases that were identified per day. So again, let's take a look at China and take away the world data. Okay. So I'm going to change the x-axis or the time axis so that we are ignoring the exponential part, and we are just looking at the time period when the curve was bending and flattening, as they say. So what you might notice by looking at this graph is what appears to be exponential decay. It's a very sharp decrease, and then it starts to smooth out and gradually flatten out and approach numbers that are pretty close to zero right around here. So what's really flattening the curve is actually that the new cases are getting less and less and approaching zero. And we can model this behavior using geometric sequences, right? It's a exponential change, which means it makes sense to use a geometric sequence here. And just to do that, we need to collect a few data points here. So let's, again, we want to try to smooth out this data. You can see that there are some jumps up and down around here. So we want to imagine that there's a smooth curve going through this section of the graph if we're going to create a model. So I'll start here on February 14th. And make note that on that day there were 4,156 new cases. And if I imagine a smooth curve going through here, it makes sense maybe to choose this point. This seems like a reasonable point to choose because if, it kind of fits between the valleys and hills involved here. So I'll take that point on the 25th of February. We had 515 new cases. So we're going to take that data and use it to make a model using geometric sequences. Here we have a model of the new cases per day measured in days after 13th of February. I say model because it is very smooth. Remember that graph we were looking at with the real world data was definitely not this smooth, and you should never expect real world data to really be exactly a smooth curved function anyway. So notice I've chosen the number of days after 13th of February as my x-axis, and the reason for that is because this pattern of decrease only started from February 13th. So we don't want to include the days before that in our model because we're only looking at this sort of shape after February 13th. Before that, the curve was, if we were to look back in time a little bit, it was actually, sort of up here and would have been more of a hump shape. But we're only looking at this part here. So again, we're going to try to model this using geometric sequence. So to do that, we need some terms. So February 14th is one day after February 13th, so we can think of this as x equals 1, and the number of new cases on that day was 4,156. And for February 25th, that is 12 days after February 13th. So we can think of that as x equals 12 and y equals the number of new cases, which was 515, according to the data on the website. Okay, so each of these we can imagine as a term in the sequence. We can imagine that this is the first term, a sub 1, and we can imagine that this is the 12th term, a sub 12. And if we remember that formula for the nth term of a geometric sequence, that can be pretty handy. It looks like this. Okay, so let's see. The good news is we know the first term is 4,156, so I can substitute that here. We don't know the common ratio, but what we do know is that when for the 12th term, we know that that was 515. So we know that when n equals 12, an equals 515. Okay, so we can take that information and really plug in most of the information into this model. So let's see, an is 515, a1 is the first term, 4,156. R is still unknown, but if n is equal to 12, n minus 1 is 11. So that's what we get. And if we want to solve this equation, we can divide both sides by 4,156 and then take the 11th root. So r is equal to 515 divided by 4,156, and to take the 11th root of that, which also means to raise it to the power of 1/11. If we calculate that, it's approximately equal to 0.827. There are more decimal places after that. I stopped rounding at the 7 because after the 7 there was a 0, so that's a nice place to stop because I don't have to do too much rounding at that point. Okay, so if we know the common ratio there, we can plug that into our model and we get something that looks like this. So I'll make my model in purple. See, the first term was 4,156. Common ratio, we're going to use this number here, 0.827, and that is to the power of n minus 1. Okay, so this is our model. This model, this geometric sequence, represents the number of new cases each day after 13th of February. Okay, what's nice about this? Well, one thing that's nice about it is that it's a geometric sequence. Another thing that's nice about it is that the common ratio is less than 1. And if you recall, when you have a geometric series and the ratio is less than 1, you can actually find an infinite sum. So what we can imagine is we can ask the question, how many total cases will be confirmed after 13th of February? And the reason we can ask that question is because if you know the number of cases on the 14th and the 15th and the 16th and the 17th and the 18th and so forth, so if we're adding up A1 plus A2 plus A3 and so forth, if we imagine that we do that infinitely long, we can model that using an infinite sequence. So we can answer the question, how many total cases will be confirmed using our model. Okay, so this would be the infinite sum right over here. So take a minute and pause the video and calculate that infinite sum and see what you end up with. So it's a big number. After the 14th of February, we estimate that if the model were to continue in the pattern that we designed infinitely long, that in total we would get about 24,023 total cases confirmed after 13th of February. So now if we took a look back at the actual real-world data from China, we had this curve, and we assume that if this pattern were to continue infinitely long, then we would end up with about 24,000 cases after the 13th of February. So let's take a look at what actually happened so far and see how realistic that is. I can, let's see, change my x-axis here. On February 14th, we had 64,000 total cases, and yesterday, April 6th, we had 82,600. So if I do a quick calculation here, the difference between this number and this number is roughly 20,000. Now, if you think that my estimate was about 24,000, that's actually not that far off, considering how simple that model was that we made. So, the difference between 20,000 and 24,000, it's tragic in the sense that there are 4,000. The difference between those numbers is 4,000 people who came down with what could be quite a serious illness. But in terms of the sheer mathematics between those things, 24,000 and 20,000 are not really vastly different numbers. So the model itself seems to be fairly reliable. Now, what's important to remember is that it's a model, and what happens after April 16th can depend on lots of things. It's not guaranteed that this pattern will continue. Let's hope it does. The people of China and the world have been through quite a bit, and we have a lot to learn from how things went in China and how things are going around the world right now. But let's hope that this clear exponential decrease continues in China, and let's hope that other countries around the world are able to get a graph very soon that looks like this.